take a look at this slide, pause the video, read through, and try to fill in the blanks. You should know enough to fill in these blanks. All right, these are important facts to have written down. Particles that have more charge when they are next to another particle. Particles that have more charge will experience a greater force. So if you put two charges near each other, the bigger their amount of charge, the greater the force they feel. Here these two would repel, and these two would repel a little less. Or sorry, these two would attract. They're opposites. But the force created would be less than the force here. The smaller the distance between particles, also the greater the force. So charged particles that are separated by a smaller distance, so the closer they are, the greater the force between them. And finally, Newton's third law says that the force on each particle will be the same. So how much ever force this Q puts on this one over here must put the same back. The charged particles put the same force on each other. So forces between the particles, or the charges, are equal and opposite. Equal and opposite. All right, make sure you have that down. Pause the video if you need to. This question I asked you is your pre-reading question. Which pair of charges do you think would feel the strongest repulsive force? So let's talk through this. First of all, pair 1 will not feel a repulsive force. They are opposites and they will therefore attract, so it cannot be that one. Let's look at pair 2 and 3. Pair 3 would have a bigger force than pair 2 because the charges are bigger, and it would only take one charge being bigger, so if this was negative 2q and just negative q, it'd still be bigger. So pair 2 is not the biggest. Now let's compare 3 and 4. Well, this one has repulsive force and 2q and half the distance. So bigger charge, smaller distance. This one is bigger than 3, so pair 4 wins. Greatest repulsive force because they're closest together and they have a bigger charge than the others. Closer and bigger charge. But now, in this example, it would not be so clear. And you're going to look at this one in your post-reading question. Notice that there's double one charge, so you might imagine like the force getting doubled, and we half the distance. Well, halving the distance makes the force bigger, so you might imagine the force doubling there too. So it's not clear which of these two would have the greater force, or if they'd have the same. Think about that for a second. So what we need is an equation that tells us exactly how much force is created between any two charge. Here's the equation. It is called Coulomb's law. Force, electric force measured in newtons, is K, a constant, times the two charges, Q1 and Q2, divided by the distance between them squared. So it's F equals K times each of the two charges divided by the distance between them squared. Force is, of course, measured in newtons and can therefore be used just like any other force to find acceleration and used in a free body diagram. K is a constant. I've heard it called Coulomb's constant before, but it's a constant. And the number for K is just 9 times 10 to the 9th newtons times meters squared over Coulomb squared. Don't confuse this with K for like spring force or spring kinetic energy, completely different K. Here K is just a number, 9 times 10 to the 9th Newton meters squared over Coulomb squared. Charge has the unit coulombs, or C. Charge Q is coulombs, and distance is measured in meters. For reference, K is actually calculated from another constant called epsilon naught. And if I remember right, epsilon naught is called the emissivity of free space. That's how much like empty space can transmit information. And K is 1 over 4 pi times epsilon naught. But that's just more of a reference that could come up in, say, a multiple choice question. We'll start looking at Coulomb's law kind of simply, using what are called factor change examples. So let's talk about how much, if one thing changes, it influences another. So here are two questions we're going to try. The first question says, and I'll number these, whoops. The The first question says, by what factor does the electric force change if one charge is doubled? So we're talking about a change here, which means we need to refer back to the original equation. F equals K Q1 Q2 over D squared. So when you're looking at changes, the first step is always just to write the original equation. And then you're going to plug in the change. So it says if one charge is doubled, it means I get to pick one, so I'm just going to double one of the charges. Step 2, we'll plug in the change. F equals K, and I'm going to double Q1 times 2 Q1 Q2 over D squared. Now in this example, it's pretty easy to see that if this side gets doubled, your force would also get doubled. So the answer here is it changes by a factor of 2. Now let's try problem number 2. And I'll start this one in a different color so we can see the different problems. Problem number 2. By what factor does the electric force change if distance is doubled? So again, step 1, I just write the equation. So step 1, F equals K Q1 Q2 over the distance between them squared. And the distance is doubled. Now since distance is squared, notice this, since distance is squared, whatever happens to it will be squared too. So when I plug in the change for step 2, we'll look something like this. F equals K Q1 Q2 over 2 D squared. And now that 2 here will get squared, so let's write it out with that kind of expanded. F equals K Q1 Q2 over the 2 gets squared, becomes 4. D squared is just D squared, like X squared is X squared. And now, a little harder to tell, this is on the bottom of a fraction. Since the top part didn't change, we'll say the top part changed by a factor of 1, it did not change. And the bottom part changed by a factor of 4. So overall, our change was by a factor of 1/4. That's how much the electric force changed. So if I increase the distance, I cut the electric force by a factor of 4. So it's 1/4 as strong as it was before. If I double one charge, I double the electric force. Now here are 2 examples where you actually work it out, not just tell how much something changed. What is the electrostatic force on a positive 4 microcoulomb charge that's 2 centimeters away from a negative 5 microcoulomb charge? Okay, so I'm going to use Coulomb's law to solve this problem. Again, I'll number them. Problem number 1. Electric force is K Q1 Q2 over D squared. You can also calculate electric force, Q times E, if you know the electric field. I'm just looking for force, so nothing to solve this for. F equals 9 times 10 to the 9th Newton meters squared per Coulomb squared. That's K. Q1 is 4 times 10 to the negative 6 coulombs. Q2 is 5 times 10 to the negative 6 coulombs. Divided by the distance between them squared, 2 centimeters, 1, 2, would be 0.02 meters squared. And I get that the force between them is 450 newtons. So electrostatic force is very strong. Those 2 things pull on each other a lot when they are close together. And since their masses are probably pretty tiny, they're going to accelerate really quickly. Now for number 2. If an 8 nanocoulomb charge feels a force of 100 newtons from a charge that is 1 micrometer away, what is the magnitude of the second charge? So I'm still using the equation Fe equals K Q1 Q2 over D squared. But here I'm asked to find the second charge. What is the magnitude of the second charge? So I need to solve for that. First, let's get the D squared out of the bottom. So I have D squared times the electric force equals K Q1 Q2. Now let's divide by K Q1. And I'm left with D squared times the electric force divided by K Q1 equals Q2. So now, let's plug in what we know. D squared is 1 times 10 to the negative 6 meters squared. Fe, the problem says, is 100 newtons. Divided by K, 9 times 10 to the 9th Newton meters squared per Coulomb squared. Times Q1, 8 nanocoulombs, 8 times 10 to the negative 9th coulombs, equals Q2. So now we solve that out, and I get that Q2 is 1.34 times 10 to the negative 12th coulombs, and I recognize that negative 12th is pico, so Q2 is 1.34 picocoulombs. And there we are. All right, anything you didn't understand, rewind, try the post-reading question, and have a good night.